Dear friends, welcome to this electrical engineering knowledge sharing channel, AMP Power System Workshop. Thank you very much for visiting the various sessions which have been conducted under this workshop 1 on power system protection. Today we are going to discuss session 6. Session 6 has a different part. Part 1 about the generator construction, generator connection, mode of connections, generator classification based on the various aspects, as well as generator grounding arrangement has already been discussed in part 1. Today we will be discussing part 2. Part 2 will be discussing about the generator protection, but not all this, only electrical protection part, only electrical protection due to internal or external fault, that will be discussed under part 2. And it will be continuing part 3, maybe it will go up to part 4 to include all the protection of the generator starting from small size to big size up to 1000 megawatt or 1000 megawatt. So let's discuss to the generator protection backup. Now if we look into the protection, we have already said that protection for any equipment we provide for not to protect the equipment, not to prevent the fault occurrence. Protection system cannot prevent the occurrence of a fault. Occurrence of a fault is due to external reason which is not fully under our control. We can only limit it. Protection system, intention of providing protection system in case of occurrence of a fault, to clear the fault as soon as possible, but it must be below the withstand time of the equipment. When the fault current, every equipment has a fault current withstand time. So intention of the protection system is to clear the fault current as soon as possible to maintain the continuity of the power supply to other equipment, and that time must be less than the withstand capacity of the equipment for the specific fault current for specific time. So intention of the protection system is to protect the equipment or not to damage the equipment under fault condition by clearing the fault. That is the intention of the protection system or any protection system. But you have to keep in mind, protection system cannot prevent the occurrence of a fault. That is not the job of the protection system. So with this background, let's see for the generator protection. When you go to the generator protection, generator is a rotating equipment. We have already discussed about this generator construction. Generator is mainly two part. One part is a excitation part, another is a output voltage producing part. Excitation part, which is producing excitation to maintain the voltage or KVR of the machine, that is of the reactive power of the machine, that is we call rotor, on which the DC winding is wound. And the DC winding, when it gets a DC power supply, it magnetized, and this speedomagnetomotive force is creating the AC voltage in the starter winding, which is a stationary part. This we have already discussed. Now keeping this small, and with this there is a pulling arrangement of the machine. So with this small idea of the construction, basic construction, let's see what are the various type of protection we can provide for the generator. Now if we look into the various abnormal condition of the generator, we can classify this protection class under two categories. One is the electrical category, another is a mechanical category. So let's see the electrical category. Under electrical category, all the abnormal condition we can again classify in two groups. One group is for internal or external fault of the machine. If there is a fault inside the machine or outside the machine, electrical fault, in that case, there is one group of protection functions are there. There is another group of electrical functions which is for the abnormal operating condition of the machine. This is not for the fault, there is no fault, but there is the abnormal operating conditions of the machine which can also give a disturbance to the machine. In that case, we have to isolate the machine as well. So when you go to the first part and then the mechanical protection part is there, that will come afterwards. Now when you go to the electrical two parts, one is an internal or external fault. What are the protection functions under that category? So we can divide the protection function of the generator. One is a electrical category, and second is a mechanical category. Okay. Now mechanical category, under electrical category there is a two group. One group is due to internal or external fault, internal or external fault, where the fault current will flow, external fault. And another category is a abnormal operating condition. Abnormal operating condition. These are the two categories of the abnormal disturbance can come to the machine. Under internal external fault, we can classify what are the fault under internal external fault. In the internal external fault, there are mainly three categories are there. One is a starter arc fault, phase fault, a starter phase fault. That is one phase fault. Second, starter arc fault. Starter arc fault. Then it could be rotor arc fault. These are the rotor arc fault. Then external overcurrent condition could be there. External overcurrent condition. External or internal overcurrent condition. External or internal overcurrent condition. That is another case. This is number 5. Number 5 is it could happen that this starter arc fault, starter phase fault, rotor arc fault, external or internal overcurrent, and in addition to this, machine could have a overloading condition. Okay, that is we can classify as a second category. These are the various, and then there is a interturn fault. Okay, interturn fault, that is also under internal fault condition. These are the 5 different types of fault: starter phase fault, starter arc fault, rotor arc fault, external internal overcurrent condition, and then internal interturn fault. These are the 5 categories of fault or fault function we categorize under electrical fault condition. And then if we go to the abnormal operating condition, electrical abnormal operating condition, that can also have a different categories. These are the different groups. What are the groups? And is a loading condition. That is, a loading is not internal external fault condition. It is a when the operation or operating team is operating the machine, they can load the machine. During loading of the machine, it could happen. You see, this is a generator typical as diagram. These are the 3 windings. All the phases may not have the equal load. Suppose one phase is 100 kilowatt, another phase is 80 kilowatt, third phase may be 120 kilowatt. When this type of unloading kilowatt loading on each phase of the machine, then machine we call it is an unbalanced condition. And during unbalanced condition, there is a problem in the machine. So this unbalance is one of the operating conditions. So one is a unbalanced loading. Unbalanced loading is one operating condition. Then the machine can be overloaded. Suppose this is a 200 kilowatt machine. Now you load about 250 kilowatt. That is not in the it is not by the machine fault. It is by external operating team is doing this. So that is also abnormal operating condition. That is overload. Overload is another abnormal operating condition. Number 3, you see this when the machine is operating. These are 2 operating condition. One is unbalanced operating condition, overload operating condition. Then there could be a this excitation. We are giving the machine as a 2-part. We said that excitation is giving for maintaining the voltage and the feeding the KVR. This excitation suddenly it can get lost or it can be reduced. In case of excitation loss, also machine will not able to produce the required KVR or required voltage. So that is also external situation. That is due to other external. It is not the fault, but it is due to operating condition. That is a loss of excitation. Loss of excitation is also abnormal operating condition. Then when the machine, suppose there is a problem with the turbine can be tripped or turbine can go under speed. If turbine goes under speed, immediately what will happen? Turbine is supposed to move the rotor, right? That is the job of the turbine. So instead of when the speed goes down, then its generator will be rotating a higher speed, and then it will take the power from the system to feed the turbine. Okay, if that is the case, then the reverse power will flow, and the reverse power is dangerous for the prime mover. So reverse power flow shall be prevented. So reverse power is an abnormal operating condition. That the reverse power, this is also a abnormal condition. Then another abnormal operating condition could be that lot of protection functions needs a voltage supply. Now how these voltages are given? The voltage are given from the PT, right? All the protection devices get the voltage supply from the generator PT. Suppose generator, this is the generator, we put the generator PT over here. This is the generator line side, we put the PT over here, When we put the PT over here, we put a primary side fuse. There is a fuse over here. And then the secondary side, we put a MCB. Okay. This is the secondary side. We put MCB over here. It is one phase I am showing. Now, if this fuse system is everything all right, there's no problem with the system. But if this fuse blown, what will happen? Immediately the PT supply will be missing. And if the PT supply missed out, then the protection functions or protection relays, those functions which need the voltage supply or need the voltage continuously, those functions will operate. Immediately machine will trip. But actually everything is healthy, only due to fuse failure it has happened. So this fuse failure or PT supply failure required to be protected. This is abnormal operating condition. That is also another protection functions which are under abnormal operating condition. These are the, then pole slipping is also another abnormal condition. These are the various electrical abnormal condition for which machine need to be addressed or machine need to be attended to avoid this situation. And then there is a third, last one is a overload I already discussed, and over temperature. That means a starter winding temperature or thermal effect of the winding or the winding over temperature condition also is a abnormal operating condition. That can be happen for different reason. It could happen due to interturn fault, or it can be happen due to overloading of the machine. So internal, or it may happen due to cooling effect of the machine. So machine over temperature also to be protected. These are the abnormal electrical operating condition. Now come to the mechanical abnormal condition. What to do the mechanical abnormal condition? One is under mechanical category, we have a various type of abnormal condition can happen. Even each machine has a cooling. It could be indirect cooling, it could be direct cooling. In case of air circulating machine, air will be taken from the atmosphere. Then the air will be by the blown, it will be blown inside the machine, and then air will be cooled down. Or the fan, there is a fan on the rotor also. Sometimes this rotor fan is giving the cooling effect. Suppose suddenly the rotor fan fell, then this cooling will not be there. In case of direct cooling, like a hydrogen cooling, the coil is sealed and cool hydrogen is going there. So if there is a cooling circuit has some problem, then cooling will not be there. Sometimes the cooling opening part can be get closed due to there is a blocking. In that case, cooling will not be there. If the cooling is not there, the machine temperature will goes up. This is one of the mechanical problem. Now in the machine, this big machine, there is a lot of bearings. All the bearings are lubricating bearings. So all the lube oil, which is lubricating the oil, if the lube oil goes down, lube oil tank goes down, or there is a leakage in the lube oil, in that case also proper lube oil will not be there, circulation will not be there, then bearing temperature can go up. If the bearing temperature goes up, that is injurious for the entire machine, turbine and the generator set. In that case, we have to immediately attend that problem. That is also abnormal operating condition. Then if there is a vibration, suppose there is a bearing has a wire tears, and due to that all the bearings are not in aligned, or the machine, it may happen that with the operation of the time, machine may misaligned. If there is a misaligned or the foundation bolt there is some misaligned, in that case machine could have a vibration. If the machine has a vibration, then immediately what will happen? All the bearing will be under vibration. So that also to be attended. In that is also abnormal mechanical operating condition. So all these things to be under mechanical category. Okay, these are the two categories. One is electrical category, another is a mechanical category. So now we'll discuss about the electrical category first part, that the fault, abnormal condition due to internal or external fault. So first we discuss about the internal fault. Internal starter earth fault and starter phase fault and starter earth fault. Okay. Then we'll go to the interturn fault, and then depending on the time we'll further plan how much we can proceed. We'll try to cover this session, part 2 session, within 45 minutes. Now generator, whatever the protection we have said, generator phase fault, starter phase fault, starter earth fault, then rotor earth fault, then your interturn fault, and the overcurrent fault due to external, internal overcurrent. These are the 5 protection we have said due to fault condition. Out of this, we first see how the starter phase fault as well as ground fault can be protected. Okay. Now for machine about normal practices above 1 MVA, if the it depends what type of protection we will provide, because this protection is expensive. So we have to evaluate the cost of the protection system and the machine, which we discussed on the first session 1. So depending on the evaluation, we have to decide what type of protection we can provide. Normal practice is up to from 1 MVA onward, these machines, if the generator size is 1 MVA or 1 megawatt, you can say 800 kilowatt or above, the machine are provided with a differential protection. Now differential protection has a different category. What type of differential protection will provide, that again depend on the further what is the size of the machine. Now below, but some of the critical cases where the area is supplied by the only one type of machine, maybe the machine is not 1 MVA but it is 750 kilowatt, in that case also we provide the differential protection. So in a thumb rule you can say from 750 kilowatt to onward, if the machine side is 750 MVA, kVA or 750 kilowatt in terms of the engine power, then from 750 kVA to onward machine we can provide the differential protection evaluating the cost. Now the differential protection we provide mainly for the starter phase fault as well as starter arc fault. It can protect to some extent starter arc fault as well. Okay. Now this is the main protection for the generator. Generator main and fundamental protection is the differential protection if the generator size is 750 kVA or up. So how this generator differential protection is provided? Now before going into this, we will say generator differential protection. When we put the protection relay, there are three type of protection relay. One is a normal differential protection relay. Then another is a, well, we can say protection scheme. There will be three type of protection scheme. One is a normal differential scheme. Then another is a high impedance differential scheme, and another is a biased or percentage biased differential scheme. These are the three main differential scheme we use for the generator depending on the different condition. Now the basic principle of generator any differential protection we have already discussed in the previous session. Differential, in case of differential protection, what we do, we put two CT on the two end of the machine, and then within the CT if there is any fault, immediately with the fault will be sensed by the differential relay. That is the basic principle. It is a unit type of protection. So outside the CT if there is any fault, that fault will not be monitored by the differential protection. So in case I have drawn the circuit, this is a generator 3 winding ABC. So this generator to be provided by the differential protection. Suppose the generator size is above 750 kVA. Suppose it is a 5 megawatt 5 MVA generator. So we have to put the differential protection. So this is the generator winding. Now the generator has a two side. One is a line side, another is a neutral side. So we have to keep in mind, if we want to put the differential protection for the phase fault of the starter, we need to take out all the neutral side 3 lead as well as phase side 3 lead to the terminal box where we have to install the CT. If we do not bring the neutral side inside the box, then the installation of the CT will be difficult. It will not be possible. In that case, the protection may be difficult to provide this type of phase fault differential protection. So when we are planning to give the phase fault of starter winding by differential protection, we have to tell the manufacturer of the generator, neutral side terminals of the generator shall come to the neutral side terminal box where this 3 CT will be mounted. This 3 CT will be mounted, or we have to install inside the neutral. In this 3 phase will come to the either the resistance element or in a separate box where the CT should be mounted, and then it will be shorted for the grounding. That is the arrangement to be made accordingly. So this is the two set of CT as per differential principle, and this is the generator. So any fault within this area will be captured by the protection relay by this 2 CT. Okay, that is the basic differential. I can redraw once again over here. As we said before, I will draw only one phase, not the 3 phase. Suppose this is a generator, this is one phase of the generator, this is a generator. So we have a CT over here, we have a CT over here. These CTs are connected. Suppose this is grounded, and then this is a protection relay is connected between this 87G. This is the basic circuit we draw. If there is any fault here, suppose the current is flowing from here to P1 to P2, and this is a S1 to S2, right? So when the current flowing through this, CT secondary current will come over here. When there is no fault inside, both I1, this is I1 and this is I2. I1 equal to I2, right? So this I1 current is coming over here. This I2 current is coming. This is the CT secondary side. So this current is coming through the relay. And in this case here also the current is coming. This is a S1, this is a neutral point grounded. And then this same current and this current is coming through this way, because this is going this way. So this current is coming this way. This is going this way, current is coming this way. So this is a I2. So I1 and I2 both are equal, so relay will not operate. But if there is a fault over here, immediately what will happen? This current will go, and there is no current over here. So only this I1 current will go and the relay will operate. That is the basic principle we have already discussed. Here the same way, that's why we have put 3-phase relay. So if there is any fault inside the CT somewhere here, suppose the winding is faulted or these two phases are shorted, then there is a phase fault. Immediately the current from the generator, suppose this is at the end of the winding, the fault is there. If the end of the winding here is 100% voltage is developed, so with this 100% voltage, immediately the short circuit current will be flowing through this CT this way, is circulating this way. So both this CT will see the fault current. When that means these two relay immediately, which phase, this is a B phase and C phase. So B phase and C phase relay will operate. And immediately the corresponding, suppose there is a breaker over here. So this will give the tip command to the breaker. Breaker will operate. Immediately, if the breaker operate and immediately it will stop the turbine also, then the generator will stop the production. Okay, because without stopping the turbine, you cannot prevent the fault. So under differential protection, when the trip protection operated, immediately this will be tripped as well as the turbine will be stopped. Turbine fuel valve should be open or closed. That is to be done. Okay, so this is a normal differential protection. But this normal differential protection has some problem. What is the problem? So this is for the low machine, low capacity machine with the expensive mode of protection we cannot provide. We can put this normal differential skip. Now in the case of normal differential skip, problem is here this relays, you see there is a two set of CTs. Now if there is a heavy through fault, suppose there is a fault outside the generator here, suppose there is a fault over here, so we are now going to second high impedance differential protection. Why we need the high impedance differential protection, that I am trying to explain. Now in case of if there is a fault outside the generator area, suppose this is the protection zone, outside the protection zone there is a fault, and this fault is a heavy fault, a high fault current, maybe 20 times fault current is flowing by the generator. In that case, if this CT is not properly designed, is not proper quality of the design, there is a mismatch in the CT, it may happen one of the CT getting saturated. Okay, CT saturated means the CT you give the magnetizing current, there is no voltage. That means what is happening over here? That means this CT is shorted, means there is no impedance. You know, CT can be represented by two resistance. One is a resistance, another is a magnetic inductance. Magnetic inductance is or magnetic reactance is responsible for what? For producing the CT secondary voltage or magnetomotive force or magnetic induction. So if the CT saturated, this part, inductance part of the CT will be zero, and this is the major impedance of the CT. CT major impedance coming from the magnetic inductance part. This resistance part is very negligible. So equivalent of this, if we say RCT under, if this is the resistance, we can say impedance, we can put in the simple resistance form. If this is the resistance of the equivalent CT, and if the CT gets saturated, this becomes zero. So effectively RCT is approximately zero. So that means CT has no resistance. So in that case, what happens? This CT can be shorted. That means to the relay, if this is the relay, then what will happen? It will showing this only the lead resistance from the CT. This conductor or cable is coming to the relay. Only that lead resistance will appear to the CT. So under this condition, what will happen? If one of the CT gets saturated, other CT is maintaining its healthy condition, then what will happen? When this external fault is there, this CT gets saturated, means it is not transferring any current, because when CT is saturated, what will happen? You give this magnetizing, it will not produce any current, because as you give the more and more voltage, no current will be produced, because it is shorted, because it is saturated. So it cannot go further current. So it cannot produce any current. So what will happen? Only this CT will be producing the current, and this CT will not produce you current. So on the CT secondary, from this side, there is no current coming to this. Only this CT is giving the current. This CT, this is giving current. Suppose this is C element, and this CT is not producing any current. Okay. So this, what will happen? This relay will operate, because only this CT is giving current. This CT is not giving current due to saturation. So to avoid this, for normal differential protection, this can happen, and then the relay will be unnecessary. It will be operated. The differential protection will not be stable. To avoid this thing, what do? We put a high impedance circuit. When this current or the voltage we calculate here across the relay, how much voltage is there. If that voltage, for that voltage, whatever the current flowing through this current will go to the CT short circuit. If we make this path is a high impedance path, then this, whatever the voltage appear due to the fault current, whatever the voltage appear over here, and then CT saturated is another part. If this CT is a zero circuit, then what will happen? If it is high impedance path, entire current will pass through the CT and return back. In that case, it will go through the relay. It will not pass through the relay. So by making the relay path high impedance, we can avoid this CT. If CT gets saturated, in that case, relay will not operate. That is called high impedance differential circuit. In that case, what we do? We put another resistance. Suppose I am showing one of the phase over here. This is a point, and here the relay, this way is coming current I2, this way is current I1. So difference of current I1 minus I2 should flow with this. In the normal condition it is balanced, but when CT gets saturated, this I2 will not be I2 equal to 0. Only I1 is flowing. But this I1 we put as, what we'll do, we put a high resistance over here. We put a resistance over here. One resistance, suppose this resistance is called RS. This is a stability resistance. So by putting the resistance this path, in all the three phases we have to put this resistance, okay, in this way. Now with this resistance, now this relay has, this path has a total this amount of resistance. If this resistance is become, or this impedance is very high, then what will happen, when this is the relay path, there are two paths. The current is coming from here. This is a one path through the relay, and then another path is short circuit path through the CT. This is a small resistance over here, that is a saturated CT. Yeah? This is a, and this is a correct CT. Okay, this CT is giving the current. Okay, this CT is giving the current. It is coming to the relay circuit, and parallel this is a saturated CT resistance. Okay, it is very small. So when this current will come, and this is a, we make it, this relay circuit we made a high impedance. It is a Z is very high. Okay, so the current come over here. There are two parallel paths. It is a very low resistance path, and this is a high resistance path. Automatically current will come through this. That at that case, even though one of the CT is saturated, the total current is producing by other CT is not going to the relay, it is passing through this. By this way, this circuit we can make a stable. So that is called high resistance or high impedance differential scheme. This scheme we provide to avoid this CT mismatch and saturation of the CT. Now we can calculate the resistance, how much resistance is required. Okay, to calculate the resistance, what we have to do? First we have to calculate, in normal case, what is the voltage coming across the relay coil. Suppose this is a relay. So when the relay is connecting in this way relay is connected. So in this case, how much voltage coming across this? If we see the equivalent circuit, one of the CT gets saturated. Okay, if that CT gets saturated, so this has no resistance. So this path is this path, and the other part of the CT, how is it? So that is, I am showing over here the healthy part of the CT. If we look this circuit, then from the healthy part of CT, this is your CT, right? This is the healthy part of the CT. This is the RCT. It is a healthy part. So but this CT is not saturated. This CT is RCT. Then from the RCT is coming to the lead resistance. This is a lead resistance RL. Okay. Then it is going to the relay coil, right? It is going to the relay coil, and then it is coming back, another RL lead resistance coming back to the CT, healthy CT. That is the way. Now this is very, very small, this part. So effectively, how much equivalent resistance here, if you calculate RCT, all are connected in series, plus 2RL, right? This is the equivalent resistance of this path. So this is the this RL. So this is the equivalent part. Now what we can do here? Now this equivalent resistance, what is the current flowing through this? In that case, this fault current. When the external fault is there, total fault current is flowing through this. The corresponding secondary fault current, I say I fault. So this into IF, that will give the voltage VF across the relay coil. So this is the voltage. So under CT saturation condition, this is the voltage appearing across the relay coil, which is responsible for producing the relay operation. So now this voltage, under this voltage, this CT should not saturate. That is our requirement. So for the, we told that during selection of the PX class, for the differential protection, we said CT shall be PX class. And PX class CT, we need to specify the knee point voltage. So here is the application. From this we can calculate for the fault current, what is the voltage produced in the circuit. The CT should not saturate with this voltage. That's why CT knee point voltage, now we can decide from this equation, CT knee point voltage will decide in such a way that that voltage must be more than this voltage. Must be more than this voltage, so that CT will not saturate. So that voltage normally we put 1.5 times to 2 times of this VF. Okay, that is we call V knee point voltage, or you can say VS or V knee point voltage. That is equal to suppose 2 times of VF. If we can select the knee point voltage of the CT, 2 times of VF, that is the VS, then CT will not saturate. So under this condition, we can give the setting of the current, or the fault current. Suppose this is the fault current IF. So under the IF, this relay should not operate. Therefore, we have to give a setting current in such a way, so when this I current will be passing through this, relay will not operate. So we will give some setting of the current which is more than this. So what is that is suppose IS. So if we give this setting VS and RS to the relay, then we can see effectively how much impedance will be coming across this. So for this impedance or the resistance, equivalent resistance, that equal to how much in this total circuit, if the voltage setting is Vs and current is Is, so that equal to the total resistance of this path, right? Now out of the resistance, if we deduct this impedance of the relay, suppose the relay impedance is Rr, then the stabilizing resistance how much? Rs equal to R, that is the total impedance, minus Rr, that equal to Vs by Is, that is the setting voltage, setting current, minus Rr. From this we can calculate the stabilizing resistance, and as well as we are calculating and stabilizing resistance calculated based on the knee, this is the knee point voltage, okay, and this is the setting current to the relay. So with this, or it is a through fault current, we can give some margin with the through fault current, because through fault current we are putting I1, we are considering. By calculation we can calculate how much through fault current. With that you can put some margin so that you will be overprotected. So from that equation we can calculate the stabilizing resistance, and if we put the stabilizing resistance, even one of the CT gets saturated, this relay will not operate. So this is a called high impedance differential scheme. Now with the high impedance differential scheme, it can be used for the directly these generators which are connected directly to the bus bar. Okay, there is no interposing any other equipment. Suppose this is the bus bar. This is we call directly connected generator. The last session we have shown the classification of the generator depending on the connection. There are two type of generator connection. One is a directly connected generator, another is indirectly connected generator. In the case of directly connected generator, what I show, directly connected generator, suppose this is a generator and then it is going to the circuit breaker, it is switched, and this is a grounded. Suppose it is a grounded through resistance. So this is a directly connected generator. So this type of either normal differential scheme or high impedance differential scheme we can use for the directly connected generator. But this normal differential scheme or high impedance differential scheme we cannot provide for unit connected generator. Unit connected generator, how it is? There is a generator transformer, then it is going to the switchyard, and then there is a unit connected transformer for unit supply, and this is a generator transformer, and this is a unit transformer, and this is your generator. Okay, so this type of connection, when this is the arrangement, in that case we cannot put this either normal differential scheme or high impedance differential scheme. Why? Because there is a lot of issues over here. When this generator connected to the generator transformer, now this generator transformer supplying the load, suddenly load thrown off due to for any reason, then immediately generator transformer will going over voltage, because at the load thrown off it will go immediately over voltage. When the over voltage will be there will be overfluxing here. Due to overfluxing, generator will see the imbalance condition, and generator it can trip immediately. If we use the normal differential scheme or a high resistance, high impedance differential scheme, this relay will get imbalance due to this magnetic inrush or this overfluxing condition. That is one thing. Second point, in this condition, this you see this what I said, this Bs or knee point Bs voltage setting is dependent on what? This is a fixed, but this part lead resistance is not in our hand. In case of here, the CT will be located in the switchyard from the switch, because this is a generator transformer locating outside from the power station, from the turbine area. So from the CT is located in the switchyard. From there, the switchyard, the conductor will go to the control room where the relay panel is located. On the other hand, this generator CT is located over here. In this case, if you want to protect the differential scheme for this, the CT will be like this. This is one CT after the neutral side of the generator, and one CT after the GT transformer. So this GT transformer location wise, it is located in the near to switchyard, and this is located where? In the turbine room. Now from the generator turbine room, this CT cable is coming from one place, this CT cable is coming from another place. To control the lead resistance is not possible. Though the CT we know the CT, but the lead resistance we cannot control. This lead resistance we cannot control. It will be not identical. In that case, you see the Vs will not be constant. Then Vs can be variable. So during execution time, in the design stage we put this, but when we lay the cable, we see it is not equal. In that case, we cannot balance it. Then this field current will be going through the relay will operate. In that case, the normal differential or high impedance differential scheme we cannot use. In that case, we have to use a relay which can maintain this, which can help or which can take this difference value of the CT lead resistance, as well as which can take care of this over voltage condition or overfluxing condition. Because overfluxing, another problem, Overfluxing, when the overfluxing is there, the overfluxing current, if you see, it contain a fifth harmonic, and fifth harmonic is dangerous. In the case of fifth harmonic, the normal differential relay will operate. In that case, we need another scheme which is called bias differential scheme. In that case, what will happen? Relay will be biased. When the fault current will go, differential fault current will pass through the relay. For up to any fault current, it will not operate. It will give some restraint up to certain 5% of the fault current. Whatever the setting value of the 5% of the full load current of the machine, or setting of the current, 5% of the setting of the full load current, if we give up to 5% imbalance current or differential current, relay will not operate. We will give some bias. In that case, disadvantage is relay will not be very sensitive for the some near to the fault, but for the high value of fault, it will be sensitive. So that is we call bias characteristics or restraint characteristics. We will include in the differential protection another feature which is called restraint characteristics. How we do that? In the case of electromagnetic relay, what we do? In the case of electromagnetic relay, you can see I am drawing one phase only here. Suppose this is a generator, okay, and then this is a CT. So this is grounded, and this is a relay is connected over here, okay, 87G. Now, in case of restraint characteristics, how we do? We put some resistance over here on both sides. This is a restraining resistance. So when this fault will take place, if this will give the restraining torque. You can say this is another coil or another electromagnet where the restraining force is given, and then the relay operating coil will be slightly delayed or it will be retarded. So in the digital relay, we can do by programming this restraining function. So when we put the restraining characteristics in the relay, then immediately relay characteristics will get changed. Okay. So this is in the case of electromagnetic relay, we put a parallel resistance, we do the restraining, and in the digital relay, we can make this programming, we can make the algorithm so that these restraining characteristics can be included. In that case, what we have to do how the restraining characteristics will do, we'll draw a restraining characteristics of the relay. Then it will be more clear how it is restraining. This is I am drawing on restraining characteristics. So this is this side we are putting this. This is your differential current. The current between these I1. Suppose this is I2 and this is I1. So difference of current I1 minus I2. That is we are plotting this way. I1 minus I2. In normal differential, whatever the moment I1, I2 some value, immediately relay will operate. That is the normal high impedance or low impedance relay. But in the case of restraint relay, for all value of I1, I2, relay will not operate. And this side we are doing this fault current, okay, IF. That equal to, you can say, I1 plus I2 by 2 average. What is I1, I2? This is suppose this is a fault. So this is a fault is outside. So this is a I1 and this is I2. Both normal case I1, I2 should be equal. So but I am taking average I1 plus I2. Will monitor this 2 divided by 2. This is equal to I fault we will consider. Okay, this way. So I1 plus I2 divided by 2 is IS in this plot. Now in the case of normal differential, what will happen? When the fault current is 0, immediately relay will operate. There is no restraining characteristics. Okay, it is instantaneous. Suppose this is a small amount of current, then relay will operate. What about the fault current is there? Immediately it will operate. When the differential current any value slightly more than 0, immediately relay will operate. That is a normal relay characteristics. But in case of restraint characteristic, it is not like this. It depends on the how much fault current is there. Corresponding fault current there will be restraint characteristic. In case of electromagnetic relay, the curve is suppose this is your 5% of the differential current. This is a 10%. This is suppose 30%. This is suppose 60%, like this. This is in between, this is suppose 50%, okay. Now, in case of electromagnetic relay, this characteristics looks like this. So, initially, this is a start from here. So, initial point, it is like this, okay. So, suppose it is 2 point, it is 3% or 4%. From the 4%, when the 4% current, this is your 150%, suppose 150% of the fault current, or it is 150% of the full load current. Yeah, the fault current is 150% of the full load current. Suppose this is a 5 times 5 into IF. This IS equal to 5 into full load current. This is a 10 times. Yeah, this is a 20 times, like that. This is the IS is represented in terms of full load current. Okay, this is equal to N into I full load. So here n equal to 1.5. So if up to 1.5, suppose the relay will not operate. Suppose this is start from, in case of electromagnetic relay, suppose this is a like this. So up to when the current is zero, when the voltage is full voltage, or the current, whatever this field current, it will not operate. When the voltage goes above 150, for this, at that voltage, it is you need to operate, you need about this amount of speed current. As the through fault current increases, corresponding speed current capacity, withstand capacity, this is your operating area. Operating area, this is a restraint area. This is a restraint area. Suppose this is a 10 times current. Suppose the spill current is this point. So this point corresponds to how much spill current? This is a spill current equal to suppose 30%. Okay. If the 30% spill current there and the total current is 10 times of the full load current, if the fault current, at that time 30% spill current, it will not operate. At 10 times of full load current, 10 times of full load current passing through the circuit, to operate this biased relay, how much spill current is required? Is must be above this point, so it will be here. That is the critical point. Suppose this may be 40%. So in that case, you need 40% differential current, then only the relay will operate. You understand? So by that way, we are giving some restraining force to the relay to avoid the operation. In case of digital relay, we do in a different way. We put this part, this characteristics part will be a square. It will be suppose like this, and then it goes up. Okay, like this. So here we have a two setting. We set as IS1, IS2. Okay, IS1 means, you see, it is a full load. Minimum 5% differential current is required to operate the relay, and it may go up to suppose 150%. Suppose this point is 150%. So up to 150% of the full load current, if the current flows through the circuit, up to 150% of the full load current, to operate the relay, you need at least 5% differential current. If the current is less than 5%, then it will not operate. It is a restraint. This is a restraint area, and this is the operating area. This is a restraint area. So suppose the fault current is spill current is 3%, and the voltage is any voltage, it will not operate. The moment current goes above 5% anywhere in this area, then immediately relay will operate. Then once, and this voltage, this is called IS1, and this is we call IS2. IS2 equal to 150% or 1.5 times of I full load. And when it goes above 1.5, immediately it is not constant, it is getting inclined. As you go more and more high current, you need more and more spill current. It is a proportionally increasing. Okay, so that is the restraint characteristics. With the inclusion of restraint characteristics inside the relay, we make the differential relay we call a voltage restraint. It is a bias. It is a restraint or bias differential relay. Now this bias in terms of percentage of the differential current we are giving, that's we call percentage bias differential relay. Now in this percentage bias differential relay, as I said, this relay we can use for either direct connected generator or unit connected generator, but it is very expensive relay. That's why it is mainly used for the unit connected generators. In addition to this, in this relay we can incorporate another characteristic that is called harmonic restraint. Why? Because I told before that when this unit connected generator is switched off, suppose the generator transformer gets switched off, then what will happen? Immediately there will be huge magnetic, there will be huge overfluxing. Then overfluxing current contain harmonics, odd harmonics, and for that odd harmonic relay can operate. So to avoid this thing, we put a fifth harmonic filter in the relay. So that is, if we incorporate the fifth harmonic filter, in that case, during overfluxing, it will not operate. That is we call voltage. It is called in that case harmonic restraint. Then this differential bias differential scheme we called harmonic restraint over differential relay. Restraint over current relay. Differential scheme. Voltage restraint, bias differential scheme. Voltage harmonic restraint, bias differential scheme. Okay, bias differential scheme, that is called. So that is a very expensive relay, and that is we use for the big size of machine or this type of unit connected generators. Okay, these are the phase fault for the major protection for the starter phase fault, and then there is a starter another protection we call a starter interturn fault. Okay, that is also we can cover today, and then we'll close it. Now a starter interturn fault, what is that? Suppose this is a starter winding. Okay, now this is this starter winding is located on the slot. Okay, so inside the slot there could be shorted between certain percentage of, suppose 5% turn it gets shorted. Then what will happen, out of 100% winding 5% is shorted, so there will be looping short circuit current. 5% voltage will be very small resistance, it will be floating, and this coil is locating inside the slot. So due to local heating, what will happen, the core can get damaged. That is one thing. Second thing, due to this short circuit, output voltage will not be balanced. Then the output voltage, what will happen, when the output voltage in one phase it has happened, other phase nothing has happened. So one phase will give a distorted output voltage, other phase will give normal voltage. So at the finally output will be unbalanced. And any unbalanced any unbalanced voltage produce a unbalanced current. Unbalanced current, when you analyze the unbalanced current, it has a three component. One is a positive component, negative component, and zero sequence component. So this zero sequence component will be producing, because this another is by differential protection, this interturn fault cannot be detected, because in the case of differential protection, what we see, this is the CT, and this fault current is flowing inside here, looping. It is not, the CT is not looking this fault current. So that's why differential protection cannot detect this interturn fault. That's why interturn fault we have to provide separate protection. So how we do that? Due to interturn fault, output voltage you will get a zero sequence current. By measuring the zero sequence current, or by operating the relay with the zero sequence current, we can protect the machine from this abnormal heating or this negative interturn fault. So how the scheme will be there? The scheme will be, there is suppose this is a generator 3 winding, okay, and then this is the 3 phase. Here is, you have a PT. Suppose this is a 1 winding PT. This is, we put on the line side, we put a PT, okay, and this PT, suppose this is a PT, and then on the secondary side we put open delta. We discussed already open delta. So open delta, normal condition, there is no voltage. In the open delta here, when the system is balanced, secondary side VA plus VB plus VC, this is equal to 0 in the case of open delta. But the moment when there is a interturn fault, there will be a voltage will be imbalanced. Okay, the voltage will not be balanced. Then immediately open delta, there will be voltage. Okay. Now problem is, in this case this PT is connected over here. Now there will be imbalance in this case. In the case of interturn fault. Similarly, if there is a earth fault, outside earth fault or winding earth fault, then also there is imbalance. And there also zero sequence current flow in case of earth fault. So how we distinguish the zero sequence current due to earth fault or due to interturn fault? That is how we are showing it. In the, you say this is a grounded through a resistance, and then this is grounded. Okay. In case of external earth fault or internal earth fault current will be flowing through the resistance and pass through this. And the most of the earth fault voltage will be dropped. Zero sequence voltage will be dropped here, V0, across the resistance in case of earth fault. But in case of interturn fault, this zero sequence voltage will be limited within the winding. So what we do over here, the PT we are not connecting across here. Normal khetre, the PT is connected over here. We connect the PT in this way. The neutral point is connected over here, not on the zero, on the ground. So whatever the zero sequence voltage in the winding, that will be sensed by this PT. And then the open delta voltage is coming. This open delta voltage, when it is coming, this open delta voltage, what we say, we have to put this open delta voltage corresponding zero sequence current to the relay. So in this case, what we choose, suppose this is a open delta voltage is coming over here, V0. I am not drawing this thing, this is open delta voltage. Then this, what do we do? Any machine, we do another thing over here. Any machine, it produces a third harmonic current in healthy condition, because due to sawtooth configuration of the starter, this starter, when it produces output voltage, the output voltage contains third harmonic current or third harmonic voltage. This in healthy condition it is there. Whether the earth fault is there or interturn fault is there or not, third harmonic current will be always present in the output. And this third harmonic current is in phase with the zero sequence current. So when we zero sequence current for interturn protection, when we passing the zero sequence current to the relay, so relay has to identify it is a third harmonic current or zero sequence current. Due to third harmonic current, you should not operate the relay under this condition. Though it is taking the zero sequence current, but it will also take the third harmonic current, which is always producing by the machine. So when the total from the delta winding, whatever the total current is coming, this is containing zero sequence current plus I third harmonic. So I third harmonic to be filtered out to operate this thing. So what do we do? I third harmonic, when third harmonic current in the delta winding, output winding, we pass to a filter circuit. So that third harmonic will pass away, will be get out. on the zero sequence will go to the operating coil of the relay. And we do another thing, in normal condition it should not operate, that's why the third harmonic current we put to a bias coil. So how do we do that? This is we put a, suppose this is a filter circuit for the, this is a RC circuit, and then this is a resistance over here, okay. Then we put a rectifier over here, okay. This is a rectifier for this converting AC voltage to DC, and then we put a bias coil. This is a voltage bias coil. So this third, and then this is a coming over here, then this is a VD, yeah? And then we put another filter circuit over here, and then this filter circuit is containing operating coil, okay. So what will happen here, this total current is coming over I0 plus I third harmonic. Now this is a, you see, this is a LC filter, this is a very high resistance to the third harmonic current, because due to L omega it will be high impedance, so third harmonic current will pass to the low resistance path through this, and it will be energizing the biasing coil. Biasing coil will be acting as a restraining, so it will not allow to operate this coil, okay. And only the zero sequence current, it will be passing through this, because it will not see any zero sequence current, will not see any impedance over here. It will come and then it will go to this this rectifier, and then it will operating the operating coil. So in healthy condition, what is happening, this I0 is not there, only I3 will be passing, and that will giving the biasing, so interturn protection will not operate. But the moment there is interturn fault, immediately this output current will contain I0 and I3. I3 will go to the biasing, that is a giving the bias, and this I0 is passing to the operating coil, and operating coil will operate, relay will operate. This is the way we provide the interturn protection of the generator. So differential protection cannot protect the generator interturn fault, because the generator differential protection CD cannot see this interturn. That's why we have to use the open delta voltage for protecting this, and the PT will not be connected to the ground point. In case of earth fault, we connect the PT over here, but here we will not connect the PT over here. We will connect the PT to this. We will be connecting the PT where, at the above the resistance, so that it can distinguish between the earth fault and the interturn fault. So by this arrangement we can protect the generator from interturn fault. I think we have already completed 45 minutes, so we will be stopping over here. Next session we will continue further. So today we discuss about the stator phase fault and the interturn fault under electrical fault condition. And with this I am closing this session 6 part 2, and thank you very much indeed for visiting this protection workshop, and I hope all of you will be continuing visiting this workshop, and thank you very much all of you. Thank you.